Last time, the file format did the heavy lifting. Parquet's row groups let Spark skip most of a file before reading a single row. But that trick only works inside a file you've already opened. What decides which files get opened in the first place is a different question, and it hides behind one overloaded word: partition. Ask 5 Spark engineers what a partition is, and you'll get 2 different answers, and both of them are correct because they're describing 2 unrelated things. One partition is a chunk of data sitting in memory, spread across executors so work runs in parallel. That's the partition from episode 1. 3,200 of them, 128 megabytes each, one per task. It only exists while a job is running. The other partition is a folder on disk, and it exists whether or not Spark is even open. Confuse the two, and you'll spend an afternoon tuning the wrong one. Start with the disk kind, because it's the one that decides how much data your job even has to look at. Our fraud feature job writes 400 gigabytes of swipes a day. Write it as one flat pile of files, and every query, no matter how narrow, has to at least list and open all of it. Write it with partition by date instead, and Spark lays it out as actual folders on disk, one per date, each holding the part files for that day. Now, a query asking for the last 30 days doesn't open 365 folders and check timestamps once it's inside. It reads the folder names, matches 30 of them, and never touches the other 335 at all. This is called partition pruning, and it happens before a single byte is read, before row groups, before any of last episode's tricks even get a chance to run. It's a coarser, earlier version of the same idea. Skip work by reading metadata instead of data. Here's the part that trips people up. Repartition 200 and partition by date sound like the same instruction. They are not. One reshuffles data across 200 in-memory chunks for the current job and vanishes when the job ends. The other writes physical folders that every future job inherits. You can repartition 100 times a day and never change a folder on disk. You can partition on disk once and never call repartition again. But disk partitioning has a trap of its own, and it's the most common way this optimization backfires. Partition by date and by merchant category both, and you get 365 dates times 200 categories, 73,000 folders. Each one holds a sliver of a day's data, some just a few kilobytes. Listing 73,000 small files takes real time, and opening each one carries fixed overhead that has nothing to do with how much data it holds. Past a point, the job spends more time on bookkeeping than on your actual query. The fix is compaction. Periodically rewrite the small files in each folder into a few larger ones, sized back up toward that 128 megabyte sweet spot. It costs a rewrite pass, but every query after that pays less in overhead. Nobody enjoys running compaction jobs. Everybody who skips them eventually finds out why they exist. There's one more thing you can do with on-disk layout, and it removes work you'd otherwise pay for on every single query: bucketing. Instead of partitioning by a column you filter on, you bucket by a column you join on. Write both the swipes and the card dimension table into the same number of buckets by card ID, say 200, and Spark can join them bucket by bucket with no shuffle at all, because matching rows already live in matching files. Get the bucket counts out of sync or bucket on a different column than you join on, and the guaranteed disappears. This only works when both sides agree. Remember the shuffle from episode 3, the network fetch that made every wide operation expensive? Joining 400 gigabytes of swipes to the card dimension table the ordinary way means shuffling that data across the network on every single run of the job. Bucketing doesn't make the shuffle vanish. Writing today's swipes into their buckets still costs a shuffle today. What it removes is the shuffle at join time. Write once, bucketed, and every query that joins against it for the rest of that data's life reads matching buckets straight off disk instead of paying the network cost all over again. That's disk layout. Partition by what you filter on, bucket by what you join on, and compact before small files eat the gain. Now the second kind of layout, and it's not on disk at all. It's what you choose to hold in memory once you've already paid to compute it. You cached it. The job got slower. That sentence sounds like a contradiction, and it's one of the more common surprises in Spark, because cache means faster is only true under a condition nobody writes down. Caching is a bet. You spend memory now to skip recomputing something later, and the bet only pays off if you actually reuse it. Cache something you touch once, and you've paid the cost of materializing it for no benefit at all. You still did the work, and now you're also holding it in memory for nothing. Now, the second kind of layout, and it's not on disk at all. It's what you choose to hold in memory once you've already paid to compute it. You cached it. The job got slower. That sentence sounds like a contradiction, and it's one of the more common surprises in Spark, because cache means faster is only true under a condition nobody writes down. Caching is a bet. You spend memory now to skip recomputing something later, and the bet only pays off if you actually reuse it. Cache something you touch once, and you've paid the cost of materializing it for no benefit at all. You still did the work, and now you're also holding it in memory for nothing. Here's where it goes wrong on our own job. The raw 400 gigabytes of swipes gets read once, then filtered down to the roughly 2% that last episode's columnar format already made cheap to read. Cache the data right after the filter, before that filter runs, and you're holding nearly 400 gigabytes in memory to save a reread that was already fast. Cache it after the filter instead, and you're holding a few gigabytes, and if 3 downstream aggregations all branch off that same filtered set, each one skips redoing the read and the filter. Same word, cache, completely different outcome depending on where you call it. Caching isn't one setting. It's a choice of storage level, and the default isn't always the right one. Memory only is fastest, but if the cached data doesn't fit, the parts that don't fit are simply dropped and recomputed on demand next time, silently, with no error. Memory and disk spills the overflow to local disk instead of dropping it. Slower than memory, still far faster than recomputing a join from scratch. There's also a serialized option, trading a bit of CPU time to pack the cache data smaller, which matters when memory is the tight resource and disk isn't. None of these is universally correct. The question is always the same one. What happens to the data that doesn't fit, and is that an acceptable cost for this particular job? And caching isn't free even when it's aimed correctly and the storage level is right, because of something from 2 episodes back. Cached data lives in storage memory, and execution memory can evict it under pressure to make room for a join or an aggregation. That eviction doesn't lose your data. It gets recomputed from lineage the next time something asks for it. But it does mean an aggressively cached job can quietly steal room from the exact computation it was supposed to speed up, causing more spilling, not less. Cache what's expensive to recompute and genuinely reused. Don't cache out of habit. And don't cache immediately before a single downstream shuffle you're only going to trigger once. There's nothing there to reuse. So, the big picture. In-memory partitions are units of parallel work, and they disappear when the job ends. On-disk partitioning is a folder layout, and it outlives every job that reads it, which is exactly why it's worth getting right once rather than compensating for it forever. Get the disk layout right, and queries skip data before they even open a file. Bucket the right column, and a shuffle that used to run daily runs once at write time permanently. Get caching right, and repeated work never happens twice. Get it wrong in either direction, and you're either recomputing what you already paid for or holding memory hostage that a join needed more. None of this is a Spark quirk. It's the same lesson as the file format last episode. The expensive decisions are made before the query runs, not during it. Next time, the daily batch job meets a deadline it structurally cannot make. The fraud model needs transactions from the last 5 minutes, and a job that runs once a day cannot produce that number no matter how well it's tuned. What changes when the same engine runs itself again and again on data that never stops arriving?